Hi everyone, it's Professor Sebastian back again to our statistics class notes, page 58 now in section 4.4. It's the last section in chapter 4, a little bit shorter section. It really is just trying to re-emphasize many of the major points and kind of summarize what's going on with a couple new pieces of information, of course. So the main topics in section 4.4 are use linear models to describe associations only when appropriate. That means don't use a linear model, don't use linear regression when the underlying scatter plot shows that it's not linear. If it's not linear, you cannot use linear regression. That should just put a stop to everything. Compute and interpret the coefficient of determination. We will see that the coefficient of determination is actually r squared. You just take r, the correlation coefficient, and square it. But I want you to be able to understand what it actually gives us, what piece of information it gives us. So first, some cautionary notes regarding regression. Do not use linear models to describe nonlinear associations. So we have to look at a scatter plot first. If the scatter plot shows us that there is an association, but it doesn't look linear, it looks like it follows a parabola or something else, then we cannot use linear regression to do this. The second thing is, even if we use linear regression and we say, hey, there's a strong correlation between these two variables, never, ever, ever assume that correlation is causation. In fact, capitalized letters, bold star, correlation is not causation. An association between two variables is not sufficient evidence to conclude that a cause and effect relationship exists between the variables. Beware of outliers. Beware of outliers. Remember, these are guys that don't really follow the line that it looks like the rest of the scatter plot's following. They can have a big effect on R. I showed you an example of if I added an outlier to that data set on mileage versus fuel consumption, that all of a sudden there was like no correlation. R went from 0.93 or whatever it was to 0.05. So it's just, you have to be really careful of outliers. Always check the scatter plot for outliers. And lastly, something we have not talked about yet, do not extrapolate. Do not make predictions beyond the range of the data. We can never be sure the linear trend will continue beyond the range of the data. This is so important. Again, bold capital letters. I want to show you an example of what I mean by that. Still referring to the association between the heights and weights of a group of 6 people. Remember, we had that where we had height trying to predict weight, and we came up with this regression line equation. Y equals B plus mx. Weight equals minus 442.882 plus 9.029 times height. What weight does this equation predict for a woman who is 36 inches tall? Let's say we have a really short woman, okay? That would predict her weight to be minus 442.882 plus 9.029 times 36, or negative 117.8 pounds. It doesn't make any sense. Right now, why is that not sense? Why does that not make sense? Why did this not work? It's because the range of the data for the women was between 61 and 68 inches tall. We only had 6 data points, and all of those 6 people were between 61 and 68 inches. So we can't assume, one, whether it was all women, and 2, whether the women we can't assume that will work for any woman outside of that range of data. So it is not appropriate to use the regression equation to predict the weight for a 36-inch tall woman, since 36 is beyond the range of the data. Extrapolation, bad, very bad. It's one of the worst things you can do in mathematics. Okay, lastly, the coefficient of determination, which is r squared. Coefficient of determination is the square of r. Whatever r is, you just square it. R is the correlation coefficient, remember. It is usually converted to a percentage, so it's always between 0% and 100%. Even if r was negative, if you square it, the negative sign becomes positive. So it's always between 0 and 1. If you make it a percentage, it's between 0 and 100%. It measures how much variation in the response variable y, how much variation in y is explained by the explanatory variable. So the larger r squared is, the smaller the amount of variation or scatter about the regression line there is. So for example, suppose data on a car's age and its predicted monetary value produces a correlation coefficient, r, which is negative 0.778. So we have a fairly strong negative correlation. As x increases, y tends to decrease in this case. So let's compute and interpret r squared. R squared, we just square this number, the negative sign becomes positive. Squaring 0.778, whenever you square something less than 1, it becomes a little bit smaller, so it's 0.605. Now, if I turn it into a percentage, I just multiply it by 100, so r squared would be 60.5%. So what happens? How do I interpret that? The car's age explains, so X was the car's age, it explains about 60.5% of the variation in the car's monetary value. So the age contributes about 60.5% of the information of the differences you see in what the car is worth. Okay, but there's other things other than the car's age. How well did people take care of it? Did it sit in a garage, or was it outside all the time? Was it in an accident and it kind of got messed up? There's lots of things that could talk about the monetary value of the car, but indeed the car's age does give us about a 60%, tells us about 60% of the different values we see in the monetary value of it.